Good evening. The project is about the design of Ultra NIOS2 instruction subset architecture for the computation of dot product of two vectors. The abstract, it is the design of a 32-bit NIOS2 processor with pipelining of 5 stages. So let's see about the introduction. The NIOS2 processor is a 32-bit RISC processor, and every processor consists of the central processing unit, which is made up of the arithmetic logic unit, register file, internal buses, and the control unit. NIOS2 processor is mainly designed for the field programmable gate arrays, where the programs that are designed or simulated in the Ultra are directly downloaded to the FPGA chip. And NIOS2 is a RISC-based processor, and the arithmetic and logic operations are performed on the general purpose registers. Now, what is a RISC processor? RISC processor is a reduced instruction set computer. RISC processors are basically designed to have a minimum instructions for every operation. In that way, we achieve high and efficient performance and few microprocessor cycles per instruction, which is a very important parameter, that is the instructions per cycle or IPC. And the addressing modes in a RISC processor is only one per instruction, in contrast with the CISC based or the complex instruction set computers. Also, a special mention about the number of instructions that are allowed to access the memory. In the case of RISC based processor, only 2 instructions, that is the load and the store. Now this slide shows the block diagram of the instruction set architecture of the processor that has been designed in this project. This consists of the 5-stage pipeline registers, 4 pipeline registers for each of the fetch, decode, execute, memory, and write back. So basically every instruction has to go from the fetch stage until the decode, execute, memory, and the write back. This is the data path for any processor. Before we see in detail about the hardware design, we shall see about the instructions in a NIOS2 processor. There are 3 types of instruction formats: I-type, R-type, and the J-type instructions. So this slide shows what the I-type, R-type, and J-type instruction is. The I-type instruction format consists of one operand, the source operand, and the immediate value, that is 16-bit, represented in the instruction, followed by the target register and the opcode. Now this opcode in any of the 3 instructions determines what type of instruction it is, or what the instruction has to do, whether it has to perform a logical or, and, or a NOT operation, or whatsoever. So this project is designed or is aimed at execution of the dot vector program. So as we see here in this slide, this is the dot product assembly program that is going to be executed by this processor that is being designed. This program consists of the move IA instruction, load, add, addi, and so on, which is a mixture of R-type and I-type instructions. Now I must tell about the NIOS2 processor pseudo instructions, which are nothing but a simplified version of the machine language instructions. So in the previous slide, we had the move IA, BGT, and the sub I instructions. These are the pseudo instructions. However, when it is going to be run by the processor, they have to be encoded or broken down into simplified machine instructions. So every move IA instruction corresponds to 2 OR high ORE instructions, and sub I is replaced by the add I instruction, and BGT replaced by the BLT. So basically this program is about the computation of the dot product. What happens in brief is that ORHI percentage HI means A vector and B vector locations in the memory consists of 6 set of elements whose dot product has to be computed. So every time the higher order bits of the 32 bits. So the 16 bits will be taken from this memory location and given to the R2 register. Similarly, the ORI instruction represents that the lower order bits will be given to the R2 register. It is a means of concatenation. The same thing proceeds for the B vector and the number of elements, n. Next, since we should not forget that NIOS2 processor is a 32-bit processor and it is byte addressable. Every location is byte addressable. So instead of carrying on with the 32 bits entirely, we are taking higher order 16 bits followed by the lower order 16 bits. Next, the load instruction is used to access memory, means it reads the value from memory and stores it at R4 register. And next, this add instruction is basically clearing the register R5 where we store the final dot product. This loop execution happens the number of times until all the elements have been computed for their respective dot products. So in this case, in our program, we have 6 elements. So until 6 elements have been computed with their products and the result is added, we keep looping repeatedly, and this branch less than is made for a comparison, and the final result is stored in the from R5 into the memory location. So this was the explanation of the dot product. Now let's see about the data path. As I had explained in the instruction set architecture, there are 5 stages an instruction must go through in order to be executed completely. They are instruction fetch, decode, execute, memory, and write back. So let us see with this help of the block diagram here. Instruction fetch is consisting of the PC instruction memory. So the program counter points to the address of the location currently in the instruction memory. And when that instruction is fetched, the PC gets incremented through the adder, and the next the added value is given as the input to the PC, which is fed back. Now, when this is part of the fetch stage, next what happens in the decode stage is the instruction is broken down into the opcode, source, and target registers, and depending on whether it is an R-type or I-type instruction, the register file accordingly takes in values. In case it is an I-type, it goes to the sign extension unit, the 16-bit value, and then it is given to the pipeline register here. Meanwhile, the second instruction is fetched now. Next, after being decoded, it is being passed on to the execute stage where the ALU computes the effective address of the location in the memory at the 4th stage. Now, appropriate control signals are turned on, be it the register write or the read data, and this control unit is responsible for providing all the control signals for necessary operations. Once the result is computed by the ALU, it is given to this data memory and it is further latched back through the write back stage. In case of a store instruction, the value is stored into the memory, and in the case of load instruction, it is read from memory. So memory read signal is made high, or in the case of a store instruction, the memory write cycle is made high. So this is how every instruction is being executed in this code. So this simulation result is basically showing the effective value that is being obtained by this computation of the dot product. The 580 corresponds to the dot vector value that is being obtained. And this slide illustrates the use of pipelining. What is the need for pipelining is that it enables parallelism. So every instruction has to go through 5 stages. So each instruction going through several stages will take a long time for computing a set of program. So to enable higher operation and parallelism and also less clock time, pipelining is incorporated in the designs. So now we go to analysis. Basically, a processor's performance is measured in terms of the cycles per instruction or CPI, the throughput, and the speed up. So the higher the CPI, lesser it will be the speed up. So or IPC, which is the inverse of CPI. So for an efficient processor must have a CPI less than or equal to 1. Now we see the merits and demerits. Pipelining. In the case of pipelining, even though parallelism and higher speed is achieved, there are certain demerits to this, is that increased use of registers for storing temporary values. And another case is the hazards. There are basically three types of hazards that are encountered: static hazards, structural hazards, data hazards, and control hazards. So in case of data dependencies and other issues, we encounter certain problems where there has to be reordering of the instructions, or using stalls such that the pipeline freezes. In that way, there is a lot of time being wasted. So that is another demerit in the case of pipelining. So better forwarding and other methodologies have to be implemented in order to eliminate these hazards and utilize pipelining at instruction level efficiently. Now the conclusion. Thus, in this project, we have designed the NIOS2 subset of instruction set architecture, and the design was simulated using Synopsys VCS, and the simulation results have been submitted in the report. So I thank you, Professor Changchu, for giving me this opportunity to do this project and learn more about NIOS2 processor as well, and record a presentation of my own. Thank you all.